Today in science, we are going to begin Chapter 13, Heat and Heat Technology, with doing Lesson 1 first. Okay, there are 4 lessons. Actually, we're going to divide them up into 5 for this chapter. Today, we're going to be dealing with temperature. You should have already watched the Bill Nye video. These are all the songs that are at the beginning that I encourage you to go back and listen to, as they will help you learn the material. All right, we have 3 objectives today. When we finish the lesson, you should be able to describe how temperature relates to kinetic energy, compare temperatures on different temperature scales, and give examples of thermal expansion. Please come back and watch this video once you're finished listening to me teach the lesson, as it will help you understand the material. So what is temperature? Scientifically speaking, it is the measure of the average kinetic energy of the particles in an object. If you'll remember, kinetic energy is energy that's in motion. So kinetic energy is the energy of motion. All moving objects have kinetic energy. We also learned in the last chapter that the amount of kinetic energy an object has depends on 2 things: the object's mass and the object's speed. So all matter is made of atoms or molecules that are always moving. The faster the particles are moving, the more kinetic energy they have. The more kinetic energy the particles of an object have, the higher the temperature of the object it would be. So the faster they're moving, the more kinetic energy. The more kinetic energy, the higher the temperature. Make sure you go to Brain Pop and you watch the video on temperature and complete the quiz as well. Here we have a still shot of molecules in motion. And if you'll notice, the one on the left, they're spaced out a little bit further and they're not moving quite as fast, because you can tell the line behind them, that little blur, is not as much as it is on the right. So the gas particles here on the right have the higher kinetic energy than those on the left. So the gas on the right is at a higher temperature. And you can come back and watch this molecules in motion animation to actually see the molecules when you apply heat and less heat and what happens to them with their motion. So the motion of particles in matter is random. So no individual particles have different amounts of kinetic energy. So random motion. The individual particles are not the same. They have different amounts of kinetic energy. So when you measure an object's temperature, you're actually measuring the average kinetic energy of the particles that are within that object. Learn something new. We, of course, use thermometers when we're measuring temperature. And this is due to a property called thermal expansion. We learned thermal means heat. So thermal expansion is the increase in volume of a substance in response to the increase in temperature. So in other words, as a substance's temperature increases, its particles move faster and spread out. I like to call it, don't touch me, don't touch me, don't touch me. It's like they're so hot and so agitated, just like when you get hot, you don't want anyone to touch you. So as a substance's temperature increases, increases, its particles move faster and they spread out. Don't touch me, don't touch me, don't touch me. You're going to come back and watch this video. It will help you understand what I just taught. There are 3 temperature scales. Celsius, represented with degrees Celsius, degrees capital C. Fahrenheit, which is what we normally use here in the United States, so degrees Fahrenheit, capital F. And then the Kelvin scale. This is the official SI temperature scale. So the international system that most other countries use, yeah, that's what they use, this in Celsius. But if you're like a really true scientist, you use Kelvin. The lowest temperature on the Kelvin scale is 0. Notice there's no degree after it because you don't say 0 degrees Kelvin, you just say 0 Kelvin. And that temperature would be called absolute 0. Here is a comparison of Fahrenheit to Celsius to Kelvin. So let's start with Fahrenheit. When you take your temperature, the norm is 98.6. If we used Celsius, that same thing would be 37 degrees. In Kelvin, it would be 310. We know that water freezes in Fahrenheit at 32 degrees. That's that magical number we're looking for to get those snow days because things start to ice over. Above 32, things are still good. 32 degrees, magical number, starts freezing, and that would be 32 degrees Fahrenheit. 0 degrees Celsius is the same as 32 degrees Fahrenheit. And 273 Kelvin would be the same as 32 degrees Fahrenheit, 0 degrees Celsius. You can also see room temperature in the 3 scales and the temperature at which water boils in the 3 scales. You're going to come back and watch this video. It's another Eureka video. So now we're going to deal with energy or temperature conversions like we did with our energy conversions. So a given temperature is represented by different numbers on the 3 temperature scales that we just looked at. And of course, you can convert one temperature scale to another, and you would use these equations to do that. I'm not going to make you memorize the equations, but just know that it is possible to convert any temperature to another one. So how is this practical? Why do we need to learn about temperature? So one practical thing would be the expansion joints on highways. If the weather is very hot, we know that those molecules are going to heat up and they're going to start moving really, really fast. Don't touch me, don't touch me, don't touch me. So the bridge can heat up enough to expand. If they did not have expansion joints, as the bridge expanded due to the heat, it would be in danger of breaking. So engineers use expansion joints to keep the segments of the bridge apart so that they have room to expand without the bridge breaking, which would be a very bad thing. Same would apply to when you lay concrete. You have expansion joints in the concrete. All right, bimetallic strips in thermostats. Have you ever wondered how your automatic heating and air in your home, how it just knows to come on and go off? Well, it's made of 2 metal stacks in thin strips. And because the 2 metals that are in that thermostat expand at different rates, a strip coils and uncoils in response to changes in temperature. And we're going to look at the graphic in just a second that shows this. But when we get finished with the graphic on the next slide, you will need to view the video after that slide as an intro to our next lesson. So I'll show you what I'm talking about. So this is the end of lesson 13.1. I tell you that again here, and I tell you to view the video on the next slide as an intro to lesson 13.2a. So here are what a thermostat would look similar to on the inside. So you can see it's coiled up in both. As the temperature drops below the desired level, the bimetallic strip coils more tightly and the gas tube tilts. A drop of mercury closes an electric circuit, and that turns the heater on. So that's how it knows to come on at whatever degrees you have it set at, 68 degrees, 70 degrees. And on this one, the opposite occurs. As the room temperature rises, the bimetallic strip uncoils slightly and becomes larger. The drop of mercury rolls back in the tube, which opens the electric circuit, and the heater turns off. So just some different ways that learning about temperature would be important in our world. So remember, you're going to watch this video, and then you will truly be finished with the first lesson in chapter 13. Make sure you do your directed reading and put your answers in quizzes.